to today's quantum colloquium. So it's a pleasure to have Yunchao Liu. He's our very own from UC Berkeley. So Yunchao is a PhD student in working with me, and he has already done a lot of very interesting work in quantum benchmarking, of course, in the complexity of complexity of random circuit sampling, quantum benchmarking using random circuit sampling, and also on the learning of learning quantum circuits. So Yunchao will talk about the polynomial quantum algorithm for noisy random circuit sampling. So Yunchao.
Okay. Great, thanks, Umesh. So it's my pleasure to talk about my recent work on a polynomial-time classical algorithm for noisy random circuit sampling. This is joint work with Dorita Haronov at Hebrew University, Xun at Harvard, and Zef Landau at Umesh Vazirani from UC Berkeley. So in 2019, Google performed a quantum supremacy experiment and claimed a quantum breakthrough that could change computing. So the experiment is called random circuit sampling, and it has 3 steps. First, we use current noisy intermediate scale quantum devices to sample from a random quantum circuit. And second, because the device is very noisy and far from perfect, we use a statistical test to evaluate how good the device is performing. And finally, we claim that the same performance from the statistical test cannot be achieved classically. So later, this experiment has been replicated by USTC, and these experiments really represent a great advance in physics experiments. And from the computer science perspective, they represent a great advance in exploring the high complexity regime of quantum mechanics. So in this talk, we will discuss recent progress on understanding the computational complexity of RCS. So this talk consists of 4 parts. We will first give an overview of RCS and our main results, and then we will discuss prior work on the computational complexity of RCS. And next, we will give a proof sketch, and finally give some discussion and conclusions. So let's start with the first part, overview of RCS and our main results. So the motivation of this work comes from the extended Church-Turing thesis formulated by Bernstein and Vazirani. It says that any reasonable model of computation can be efficiently simulated on a probabilistic Turing machine. So here, efficient refers to polynomial time. Of course, this is expected to be violated by scalable fault-tolerant quantum computing. And one of the motivations for quantum supremacy is to make this happen sooner. So the goal is to give an experimental violation of the extended Church-Turing thesis using noisy intermediate scale quantum devices. And there are really 2 aspects of this goal. The first aspect is computational complexity, where the main question is, does the model of noisy random circuit sampling violate the extended Church-Turing thesis in the asymptotic sense? The second aspect is finite-size experiments, where the main question is, does current 53 to 60 qubit experiments take a lot of resources, meaning time and GPUs, to simulate classically? So in this talk, we will mainly focus on computational complexity, but we will also briefly discuss finite-size experiments. So here's the model of RCS experiments. So we have a random quantum circuit shown on the right-hand side, and each white box indicates a independently sampled random 2-qubit gate from a certain distribution. And there is also noise in the circuit, where at each step, each qubit is subject to an arbitrarily small constant amount of noise. So this is our theoretical model. And the experiment is performed as follows. First, we sample a random circuit, looked like this, on n qubits with depth d. Here we will want d to be at least log n to satisfy a condition called anti-concentration, which says that the output distribution of the random circuit should be sufficiently widespread for statistical purposes. And next, we fix this circuit and implement it on the device many times and obtain m samples from this noisy output distribution denoted by p tilde. Next, after collecting these m samples, we will compute a statistical measure, which is simply a function of the circuit as well as the n-bit strings. So in general, this takes exponential time. And later we will discuss how to deal with this exponential time for statistical verification in actual experiments. And finally, we repeat the above procedure for a few independent random circuits. Okay, so here is our main results. Consider a noisy RCS experiment which collects m samples that looks like this. So here we will do the experiment a favor and ignore the time used for classical verification. So we will only count the time in the experiment to collect these m samples, which of course is proportional to m. So we give an algorithm that can also generate m samples that looks like this, and this takes poly m time. So this could be slower than the experiment, but not exponentially slower. Moreover, the output distribution of our algorithm is so close to the output distribution of the noisy experiment that no statistical test can tell the difference between the two. Okay, so here is the detailed statement of the theorem. There is a classical algorithm that input a random circuit C on n qubits, outputs a sample from a distribution that is epsilon close to the noisy distribution in total variation distance, with success probability at least 99% over the choice of C in time poly n 1 over epsilon. So this result has some assumptions, which are anti-concentration and sufficient randomness in the gate set. So later we will discuss them in more detail. And also, this improves the previously known result of Gao and Duan in 2018, which is n to the power of O log 1 over epsilon. So roughly speaking, this improvement is important because we will see that we want to choose epsilon to be very, very small. So next, we will discuss how to understand this result. And in particular, we will show how to use this theorem to get the claim that we just showed in the picture. So the main significance of this result comes from comparing classical simulation and quantum experiments. And this is related to a very simple fact, which is consider two given probability distributions. And they cannot be distinguished by any statistical test on m samples, say with probability of 51%, if they are very close in total variation distance, and the closeness is roughly 0.01 over m. And therefore, we can choose epsilon to be this target and plug it into the theorem statement and result it in a running time of poly n and m to guarantee indistinguishability. In other words, our result says that the running time of our algorithm is at most a polynomial in the running time of the experiment in order to be statistically indistinguishable from the experiment. And of course, we should point out that currently the running time of our algorithm is not practical. It's roughly m to the power of 1 over gamma, where gamma is the noise per gate. And therefore, these results do not directly address finite-size experiments. So now, having understood the results, the next thing to do is to understand the scaling of m with respect to the size of the circuit. In particular, we will discuss the role of circuit depth. So here, the situation is that the experiment is very noisy, and we need to collect enough samples to detect a non-trivial quantum signal from the experiment. So here we have this axis, and the distance on this axis indicates the distance between probability distributions. So we have the uniform distribution on one end, and the ideal output distribution of the random circuit is far from uniform on the other end. So since we have a small amount of noise per gate, the output distribution of a noisy random circuit sampling experiment will in fact be exponentially close to uniform in total variation distance in circuit depth. So the output distribution of noisy RCS is 2 to the minus theta d, close to uniform. As a result, the experiment needs to collect at least 2 to the d samples, because otherwise we cannot even tell the difference between the experiment and the uniform. This means that in general, both the experiment and our algorithm have running time exponential in circuit depth. So this means that using a large circuit depth in RCS is not practical for both the experiment and our algorithm. However, there is a specifically interesting parameter in this regime, which is theta log n depth. So as we have discussed earlier, anti-concentration is a central assumption for both the experiment and our algorithm, and that needs at least log n depth. On the other hand, we want the experiment to have polynomial sample complexity. And this means that the circuit depth should be at most log n. Therefore, this means that theta log n depth is actually a sweet spot for scalable quantum supremacy experiments, as recognized by Deshpande et al. So this is the regime where the experiment is fully scalable, and both the experiment and our algorithm have running time that is polynomial in the number of qubits. So this is the situation of this regime. The noisy RCS distribution is 1 over poly far from uniform, with some fixed constant c here. And then our algorithm can sample from a distribution that is arbitrary 1 over poly close to noisy RCS in time polynomial in number of qubits. In the meantime, it is conjectured to be hard to sample from a distribution that is close to the ideal RCS distribution without noise. Okay, so this finishes the description of our results. And to put these results into context, next we will discuss prior work on the computational complexity of RCS. So there are two main genres of prior work on computational complexity. The first genre is what we call as ideal RCS. So here the input is just a random quantum circuit, and we want to sample from the output distribution of this circuit. And there are no noise in the definition of this quantum circuit. So here the goal is to prove that it is hard to sample from a distribution that is epsilon close to the ideal distribution of this random circuit in total variation distance. So by known reductions given by Stockmeyer and Aaronson Archipov, if we assume anti-concentration, then it suffices to show something about computing the output probability of this random circuit. In particular, we want to show that it is sharply hard to compute the output probability of this random circuit within additive error epsilon over 2 to the n. So roughly speaking, this just comes from the fact that we want to get epsilon close in total variation distance. And therefore, on average, we want each output probability to be epsilon over 2 to the n close. Okay, so this has been the goal for a line of work. And currently, we cannot prove this statement, but we can prove a statement with smaller robustness in the additive error. In particular, if we consider a random circuit sampling input with n qubits and m gates, where m is roughly n times d, then the early result of BFNV and Moasa showed average case hardness with some small additive error with a large exponent. And later, in my work with Adam Bouland, Bill Pfefferman, Zeph Landau, together with KMM21, we improved this result to exponential in minus m times log m. And later, in this year, Krobe removed the log factor and improved it to 2 to the minus om. And of course, this still falls short from achieving the goal, which is epsilon over 2 to the n. However, here, I should also say that there are several non-barrier results, as indicated by this red mark, which says that with the type of techniques that we have been using for proving these results, it's unlikely that we can eventually reach the goal. So that's roughly the picture in the ideal regime. On the other hand, the second genre of prior work on computational complexity of RCS is in the high noise regime. So here, we want to look at the different situation, which is instead of being close to the output distribution of ideal RCS in total variation distance, actual experiments actually only achieve a tiny correlation with the ideal output distribution due to noise. And this is simply a consequence of the fact that the noisy distribution converges to uniform exponentially quickly in depth. However, we want to show that this is still hard classically, because this is the regime that is relevant to actual experiments. So as an example, let's see what Google did in their experiments. So given M samples from the device, what Google did is to calculate this specific statistical measure called linear cross entropy, which is a simple linear function of the ideal output probability of these samples collected from the device. So let's try to understand this quantity a little bit. In expectation, if we are not doing anything non-trivial, if we are just sampling from the uniform distribution, then this quantity equals to 0. On the other hand, if the experiment is perfect, meaning that the samples are actually from the ideal distribution, then this quantity is related to the second moment of the ideal RCS, which is something that is larger than 0. So here, the overall intuition is that if the experimental distribution is more correlated with the ideal RCS distribution, then this statistical test tends to be larger. And therefore, it can be used as a benchmark of the experiment. Okay. So as a quick summary, in expectation, the XCB is roughly the inner product between the two distributions. And it equals to 0 when the experiment is uniform. And it equals to 1 when the experiment is perfect. And this is also related to the anti-concentration. Okay, but an issue here is that, as we have mentioned in the beginning, even with this very simple statistical test, it is still hard to estimate because it requires computing these ideal output probabilities, which takes 2 to the n time in general. However, there are ways to compute these things at small sizes and then heuristically extrapolate to large size. And there has been some arguments showing that this heuristic extrapolation works well above log n depths. And therefore, this is what Google did. And they concluded that their experiment on 53 qubits and depth 20 achieves an XCB of 0.002. And indeed, this is only a tiny correlation with the ideal RCS distribution. Okay. So now the issue is clear. We want to focus on the noisy regime, and we want to show that even the tiny XCB achieved in experiments is still hard to achieve classically. So how do we do this? In 2019, Aaronson and Gunn formulated a conjecture called XClass. And this conjecture says that even a tiny correlation of order 2 to the minus n with the ideal RCS distribution is still hard to achieve classically. So this is very similar to the previous conjecture of Aaronson Chen in 2016 called QUAS. which supports the hardness of a different statistical test called heavy output generation. So the reason that they need to conjecture this very strong parameter of order 2 to the minus n was because this was necessary to support the hardness of tiny XCB due to the fact that the reduction has an overhead. So overall, this provided a way to heuristically argue that even the very small XCB achieved in actual experiments was still a classically hard task. And indeed, this conjecture has been reasonable, and therefore it provides the evidence of high complexity in a noisy regime that we needed. However, last year, the recent work of Gao et al. Cast doubt on these arguments. Specifically, it shows that actually a correlation of 2 to the minus d can be achieved classically. And since in experiments we use a circuit depth that is much smaller compared to the number of qubits, this sort of refutes the previous conjecture. However, there are 2 points that is unaddressed by this work. Because even if the original strong conjectures are false, there could still be a weaker conjecture that still supports the hardness of noisy experiments. And furthermore, this result only specifically targets the XCB test, and the other statistical tests could still be hard to achieve classically. For example, this result doesn't say anything about the heavy output generation test. But overall, this work really reopens the question of, is there high complexity in noisy RCS experiments? And our work addressed this question by showing that no statistical test can distinguish between the experiment with M samples and our poly M time algorithm. Okay, so having introduced the prior works on RCS, here's a brief summary. So first, we show that the running time of our algorithm is at most polynomial in the running time of the experiment in order to be indistinguishable from the experiment. And in particular, at theta log n depths, both the experiment and our algorithm have polynomial running time in the number of qubits. So based on the above 2 statements, we come to the conclusion that noisy RCS cannot be the basis of a scalable experimental violation of the extended Church-Turing thesis. And here, this provides the motivation that it's really an exciting time to start developing new proposals for near-term quantum computational advantage with a better complexity foundation, such as we can try to do practical implementation of cryptographic proof of quantumness protocols. And of course, our result is conditioned on the assumptions that we make, and we will discuss them in detail later. Okay, so next, let's temporarily deviate from complexity theory and briefly discuss recent progress on practical simulation of RCS experiments. So as we introduced earlier, XCB is this statistical test that reports a number between 0 and 1. In 2019, Google achieved XCB of 0.2%. And based on the best simulation algorithm, they estimated that it would take 10,000 years classically to achieve the same XCB with the largest supercomputer. However, it turns out that since then, a lot of progress has been made with practical tensor network algorithms. And this leads to the result last year by Panchen and Zhang, which used brute force tensor network simulation to achieve the same XCB using 500 GPUs in 15 hours. However, from the practical perspective, this is really not the end of story because these brute force algorithms are inherently exponential time, and therefore they become impractical even if the system size just slightly increased by a few qubits. In particular, the largest RCS experiment currently on 60 qubits by USDC has not been challenged by a classical simulation algorithm. And of course, on the other hand, there has also been effort to try to develop efficient algorithms to achieve the same performance. In particular, the algorithm of Gao et al. Is scalable with system size, but it currently achieves 10% of the XCB of Google's experiments. So here, an interesting question is, can we develop practical implementations of our algorithm that achieves a good performance? So for now, it is too early for us to speculate about the outcome of this. Okay, so that's the situation with practical simulation. And next, let's spend some time to understand the proof. So we will start with an overview of the prior arguments to give evidence of high complexity in the noisy regime. In particular, the intuition behind Aaronson-Gunn's conjecture is the Feynman-Pass integral, which is this simple formula. So let's consider a quantum circuit, C equals UD, blah, blah, U2, U1. So each UI represents a layer of 2-qubit gates. So the Feynman-Pass integral is this simple equation that is simply a fact of inserting the computational basis in between each of the layers. So on the left-hand side, we have this output amplitude of the quantum circuit. And on the right-hand side, we have this huge sum. There are many, many terms in this huge sum, and each term is a product of small transition amplitudes that are complex numbers. So the intuition of Aaronson-Gunn is the following. So we know that each term on the right-hand side, which we call Feynman-Pass, they contribute equally on average since we have a random circuit. And there are many, many paths in total, roughly 2 to the n times d. And therefore, if we have an efficient classical algorithm, we can only sum over poly n of these paths. And since that's such a very small fraction of the total amount of paths, this only gets an exponentially small correlation with the ideal output distribution. And therefore, they conjecture that no classical algorithm can achieve better than 1 or 2 to the n correlation with the ideal RCS. Okay, so essentially, our algorithm actually looks very similar to this, except that we use a different basis. So it turns out that we just take exactly the same algorithm, Feynman-Pass integral, which we already know shouldn't work for simulating random circuits. But it turns out that it actually works if we change to a different basis, where we used actually the poly basis. So here is a diagram that shows an example of the Feynman-Pass integral. So on the left-hand side, we have this quantum circuit, and we insert a particular computational basis elements in between these layers. And this specifies a particular Feynman-Pass. And we know that the contribution of these paths are uniform. So on the right-hand side shows our algorithm, the Polypass integral. And this algorithm, and this diagram shows a specific polypath, where we can see that in each layer, we insert an element from the poly operators. Okay, so there are 2 main ideas behind this algorithm that makes it work. The first idea is that in the poly basis, these paths are actually highly non-uniform. And therefore, we can actually order them by importance and then only consider the most important path. So as we remarked here, due to noise, the contribution of a polypath actually decays exponentially with the number of non-identities, the number of x, y's, and z's in this diagram. And the second main idea is to design an efficient algorithm to calculate those important paths. So the algorithm uses the unitarity constraint that we highlighted here in the yellow, which says that in the polypath, the identity operator can only go to the identity operator. And therefore, the algorithm can be efficient enough to achieve the desired approximation error in polynomial time. And next, we will discuss both of these main ideas in detail. So let's start with the first main idea, non-uniformity of polypaths. So the idea is that let's consider the finite path integral in the Pauli or Fourier basis. Then the contribution of a low weight path is much higher than a high weight path due to noise. So here, weight just means the Hamming weight of the Pauli path, which is the number of non-identities in the path. So to understand this sentence, we will need to specify what we exactly mean by a polypath. And this involves two steps. The first step is to switch from vector basis to operator basis. That is, instead of thinking about a quantum circuit as applying unitary matrices to vectors, we think of them as applying unitary channels to density matrices. And the second step is to decompose the density matrix at each layer in the Pauli basis, using the fact that the Pauli operators are a complete basis for matrices. So now we can decompose the density matrix as a linear combination of Pauli operators with real coefficients. And then we can just think about evolving Pauli operators and combining all of these transition amplitudes. So let's consider this by an analogy. In the vector basis, we can think of a unitary matrix as mapping a computational basis element I to J. And the transition amplitude for this mapping is bracket JUI, which is a complex number. So in the Pauli basis, we want to apply unitary channels to Pauli matrices and consider the transition amplitude. So in this case, the transition amplitude from Si to Sj, where Si and Sj are Pauli operators, equals to this quantity, the trace of Sj times U-Si-U dagger. In particular, U-Si-U dagger is the evolution of the Pauli operator and the unitary channel. And then this trace is simply an inner product between Sj and this operator. So this is just an analogy of this vector basis transition amplitude. Okay, so having this, now we can write down the formula which we refer to as Polypass integral. It's very similar to the standard finite path integral with several differences. So on the left-hand side, we have the amplitude square, which is the output probability of the quantum circuit. Instead of, so this is a positive real number instead of being a complex number in finite path integral. And on the right-hand side, we still have this giant, huge sum of polypaths. And each polypath is a product of these real transition amplitudes. And therefore, this right-hand side is just a giant sum of real numbers, which can be both positive and negative, instead of being complex numbers. And we denote these polypaths by sum over S, F, C, and S. So S is just a configuration of the polypath that we showed earlier in the diagram. Okay. So with this, the idea becomes clear. In particular, if we consider depolarizing noise in the Pauli basis, it has this simple form of mapping identity to identity and non-identity Pauli to non-identity Pauli with a coefficient 1 minus gamma, where gamma is the strength of the noise. So having this, we can write down the Polypass integral as the following. So for a quantum circuit C, the Polypass integral is just saying that we can decompose the output probability of the quantum circuit C as a giant sum of the polypaths. And then if we add noise into this circuit, the left-hand side becomes the output distribution of the noisy circuit, and the right-hand side is a reweighted polypath integral, where the contribution of a polypath in a noisy circuit decays exponentially with its Hamming weight. So here, the absolute value of S is defined as the Hamming weight of S. So now the algorithm is very simple. We just compute this truncated version of the noisy output distribution. So here we have this sum over S 1 minus gamma to the power of s times the polypaths, except that we only sum over those polypaths that have low Hamming weight up to some parameter L. And it turns out that it suffices to choose L equals O log 1 over epsilon to achieve the desired approximation error. Okay, so the claim that we can just choose L equals O log 1 over epsilon to achieve the desired total variation distance epsilon is non-trivial. Because as we have discussed earlier, each of these terms in the Polypass integral, FCS, they can be both positive and negative real numbers. And therefore, it's not obvious that the more paths we calculate, the better performance it will get. However, it turns out that this is the case, and the proof for this bound uses two properties of random circuits. The first property is what we call orthogonality. This is saying that on average over random circuits, the product of two polypaths equals 0 when the polypath is different. And the second property is called anti-concentration, which is saying that on average over random circuits, the second moment of the probability of the ideal probability distribution is small. So having these two properties, we can just give a very simple proof sketch of this claim. So the proof is that we can use Cauchy-Schwarz to convert the L1 distance, which is what we want to bound, to L2 distance. And that becomes a giant square. And then we can use orthogonality to kill all the cross terms, which transfers this giant square into a sum of squares of small terms. And then we can show that this sum of square can be bounded using anti-concentration. Okay, so this is how to get the desired approximation error with the algorithm. And then it only remains to show that how much time do we need to get this approximation. And this brings to the second idea, which is efficient enumeration of polypaths. So here the key observation is unitarity, which is a very simple fact saying that if we consider a unitary as a quantum channel, then it can only map identity to identity poly and non-identity to non-identity. So let's consider this by analogy. If we consider a unitary matrix U, then the transition amplitude, brackets JUI, this in general can be a non-zero complex number for any I and J. On the other hand, if we consider the transition amplitude in the poly basis, the trace of Sj U SIU dagger, this quantity can only be non-zero when both Si and Sj are identity, or both of them are non-identity. And of course, this means that a polypath only contributes a non-zero value if it satisfies this constraint everywhere in the circuit. So clearly, for our classical simulation algorithm, we only need to worry about those polypaths that are non-zero. And therefore, this constraint dramatically reduces the computational complexity of the time in order to calculate all these relevant polypaths. In particular, the insight we use to reduce the time is called continuity, which is saying that if we look at the polypath, then the configuration of a layer of the polypath in a certain layer cannot deviate too much from the previous layer. So here is an example. Let's consider the polypaths in these two layers of the circuit. So this is a valid polypath, which could be non-zero. And we can clearly see that it needs to respect this constraint highlighted in the red circle, where if we have identity in the bottom layer, then the top layer is forced to also be identity. So if the bottom layer is not identity for some gates, such as this IX, then the top layer can be anything except identity. So this combinatorial constraint allows us to design an enumeration algorithm that calculates all of the non-zero polypaths below weight L in time 2 to the L. So this happens to be good enough because L equals log 1 over epsilon, and therefore 2 to the L equals poly 1 over epsilon. So this completes the proof of the algorithm. Okay. So now we will conclude with some discussions. The first thing is to discuss the assumptions in our main results. So we have just saw that we have these two key assumptions when bounding the truncation error, anti-concentration and orthogonality. So let's look into them. Anti-concentration says that the second moment of the output probability of the ideal RCS is small. And this statement has been proven for certain architectures and is believed to hold above log depths for general architectures. And of course, here the question is, what about sub-logarithmic depths random circuits? So clearly our result is not applicable in this regime, but there are a few things we can say about this. The first thing is that theoretically, it is even unclear if ideal random circuit sampling below log depths is hard or not, due to the fact that we don't have anti-concentration, and therefore the line of work that we discussed for ideal RCS doesn't really apply. An example here is that Knapp et al. showed that ideal random circuit sampling in two-dimensional lattices with very small depths below some constant is classically simulable, even without noise in the gates. And the second point is that existing random circuit sampling experiments relies on Porter-Thomas for the statistical benchmarking. This is actually even stronger than anti-concentration. So far, all of the experiments needs anti-concentration in order to perform the statistical tests. Okay, so the next assumption in our main result is randomness in the gate set, where we assume that the gate set is closed under random Pauli gates. And in particular, this is used to imply orthogonality, which we just show in the proof. So this statement is quite mild. For example, it holds for hard random 2-qubit gates or a fixed 2-qubit gate with hard random single-qubit gates. Of course, here the question is, what about less random gate sets? So there are a few things we can say about this. The first thing is that we need at least some randomness in the circuit. Since, of course, by definition, we are doing random circuit sampling. So we need some randomness in the gates, for example, to produce the signatures of random circuits, such as Porter-Thomas. And the second point is that currently we do not know if our main result provably works for Google and USTC's gate sets because they violate the above condition. But it works for a closely related gate set where we just insert random Z rotations on top of Google and USTC's gate set. Okay, so this concludes the discussions on the assumptions in our main result. And finally, let's give some conclusions. So the conclusion of this talk is that RCS is a really exciting experiment with multiple aspects. First, it is a very good benchmark for quantum devices because it represents a clear metric to evaluate the computational power of our current noisy quantum devices. And second, the current back and forth with classical spoofing algorithms, they really inspired continued improvement of quantum devices. So this back and forth is really a healthy development in our field. In the meantime, there are also several issues with scaling up RCS for potentially larger devices in the future. The first issue is that theoretically, we give strong negative evidence for RCS as a scalable experimental violation of the extended Church-Turing thesis. And then practically, there is also the issue of it becomes harder to perform verification as the system size gets bigger, even with these heuristic methods that we currently have. So this gives motivation to really start developing new proposals for near-term quantum computational advantage with a better complexity foundation, and hopefully also efficient verification. And one interesting thing to do is to think about how much resource in terms of qubits and gate errors are needed for cryptographic proof of quantumless protocols. And finally, let me end with some high-level remarks. So at this point, if we look back into the history, it's clear that the best thing about RCS and quantum supremacy experiments is that they provided a clear target for the field to achieve. And as a result, this actually motivated a giant leap in the development of larger and better quantum devices. So this is really a great thing. So why don't we try to do this again with the next challenge problem on the future devices? In particular, the accumulated experimental advances and the theoretical understanding in complexity theory that we have learned from RCS provides the foundation for the next challenge problem for the next generation of near-term quantum devices. Okay, and that's all I want to say. Thank you.
Great. Thank you, Yunchao. Maybe we have time for a few questions before we set up the panel. So if anybody wants to ask a question, maybe we can, you can raise your hands or just speak up. Okay, I see Venkat. Would you like to unmute?
Sure. Yeah, thanks, Yunchao. Very nice talk. I had two questions, actually. One sort of technical and one little more just trying to understand the lay of the land based on your final summary. The first question was, so I guess your algorithm has an exponent of 1 over gamma, where the gamma is the noise rate. And I guess that sort of makes sense because if it's more noisy, it becomes easier to simulate. But can you say where that dependence comes from in your algorithm?
Oh, right. So
maybe you said that and I missed it. Sorry.
Okay, so yeah, it essentially comes from here when bounding the truncation error, because we can see that here is an exponential decay with respect to the Hamming weight, but the exponent is sort of, so this is roughly e to the minus gamma times s. So if we choose some specific truncation parameter, in order to achieve the desired approximation error, it naturally have a 1 over gamma inside of this vector. But of course, this is a sort of a theoretical upper bound, and it doesn't necessarily mean that this is the optimal random time, and there's potentially room for improvements.
Great, and I guess the second question was a little more high level. I guess there is this sort of chase between doing things with this NISQ model, like this circuit sampling, and then trying to then also achieve it with classical things. I mean, is it conceivable that maybe the actual supremacy will be exhibited once you have some error correction built in, so we can go beyond this model? Or do you think already in the NISQ there should be some demonstration?
Yeah, so I think that's really up for discussion at this point, because, for example, if we want to do this cryptographic proof of quantumness, which is a very well-founded protocol, we only need to sort of go beyond certain security parameters. So it's sort of still a finite size problem. And whether we can actually do it on maybe near future devices is really up for discussion.
Okay, thanks.
Sevak?
Yeah, hi, Yunchao, really great talk, and I love the work. So I just want to ask a very simple high-level question, which is that you mentioned there's this uniform gate set assumption and how it doesn't actually break as far as you can tell, like the Google experiments in UTSC, for example. And so the simple question is, I mean, the work very explicitly says, we should not use RCS as a foundation for noisy RCS, and yet, this slide says that you haven't broken the Google experiment. So what should I take out of this? Like, is there still hope for RCS, at least for non-uniformly random gate sets, or is the Google approach broken in some sense or not, right?
Yeah, of course, strictly speaking, we cannot say anything about exactly those gate sets used in those experiments. But really, it's hard to believe that there could be a huge difference in complexity between different random gate sets. Part of that evidence comes from this statement, where this random zero rotation is sort of a simple change on top of the gate set, and it makes it satisfy the assumption. So at this point, I think it's really interesting to further investigate whether this this condition in our result is really an artifact of the proof or it is fundamental. So it's not completely clear yet, although one would expect that it's not fundamental.
Okay, so I should take it as, that the insertion of the random Z rotations is your way of saying, okay, you strongly believe that RCS really is broken in the noisy regime as far as supremacy is concerned.
In the asymptotic sense, yes.
Yes, exactly, of course. Good. Yeah, but for like extended Church-Turing thesis, that is the sense we care about, I suppose, in some sense, right?
Yeah.
So yeah, okay, cool. Thank you.
So any other questions? So Venkat, you already did you? Okay, great. Okay, so I think there was a question, the Q&A.
Let me address the.
Imply anything about simulation? Okay, go ahead.
Oh, Xun is typing an answer. Okay, so of course currently this doesn't say anything about the simulation of arbitrary quantum circuits, because in particular, the relevant part is that this bound requires randomness in the gate set. You can see that all of these statements has average over quantum circuits in front of them. So clearly, so this doesn't directly say anything about arbitrary quantum circuits, although it's interesting to further investigate maybe what kind of quantum circuits can this algorithm work, and what kind of circuits does it not work. Okay, so the second question is, what would be a good potential challenge problem for NISQ devices? One thing is what I mentioned as the cryptographic proof autonomous, but of course it would be very interesting to come up with something in between, because that still seems a bit far from the devices we have right now. So maybe some combination of RCS with some other things to make it with have a better complexity foundation. And second, would your results still hold if one were to replace total variation distance by Wasserstein type distances? So for our results, the real main motivation is to guarantee statistical indistinguishability. And for that purpose, total variation distance is the right distance. The other things may not be directly relevant for a statistical verification.
Okay, great. So maybe if you stop sharing your slides, we can move on to the panel at this point. So okay, great. Well, welcome everyone to the panel. So it's as you can see, it's a really fantastic panel, because it's sort of a who's who in random circuit sampling, starting with Scott, who of course you all know about, and he's I don't need to say that he's done more about quantum supremacy than anybody else that I know of. There's Adam Bouland, who's on the faculty at Stanford, and of course, in addition to the work he's done on the complexity of random circuit sampling, he's also, his work sort of asks this question: what does complexity theory illuminate for us in terms of physics, quantum gravity, etc. And then Sergio Boixo, who you've seen on these panels many times, he's the chief scientist at Google, and is one of the main theoreticians dealing with these questions about random circuit sampling. So it'll be, let's start with remarks from you. So maybe I don't know who would like to go first. Scott, do you want to start things off? And
sure, I can. So thank you, Yunchao. It's a really nice talk, and I'm a really big fan of this result. I think it answers, one of the big theoretical questions that we had about random circuit sampling. So maybe it would be helpful to just, maybe make some brief remarks about sort of the history of this, right? So, over a decade ago, I guess, Alex Arkhipov and I proposed boson sampling. And then, we around 2014 or 2015, Google became interested in actually demonstrating sampling-based quantum supremacy. But it became clear that they were not going to do it with boson sampling. They were building a 2D lattice of superconducting qubits, and so so our task would be to sort of adapt the theory that we developed to that setting, and and we said, okay, that's fine, we can do that. But then in 2016, it would have been, I learned about this work by Gao and Duan, right? And they were making the point that, well, if you have a constant rate of noise, on each gate, which in practice you will, then, random circuit sampling is not going to scale, right? Or rather, it will have in this sort of regime that at least that we had been thinking about, it will have a simulation that takes time polynomial in n, and and our response at that time, this was 6 years ago, was okay, fine, we're not trying to scale to arbitrary n. We're trying to do something when n is 50 or 60, right, or 70, where we fully acknowledge that if your goal is to scale to thousands or millions of qubits, then ultimately you will need quantum fault tolerance. Okay, right, and this point came up in the Q&A also, right? And we said, what is actually the goal with these random circuit sampling experiments? The goal is to do an experiment that sort of directly shows you that you are exploiting an enormous number of Hilbert space dimensions for computational benefit. Right. So in the case of Google Sycamore experiment, it was a Hilbert space with 2 to the 53 dimensions. That's like 9 quadrillion. Okay. And and as was pointed out in the Q&A, right, we still do not have a sort of efficient classical spoof of that experiment, efficient in the sense that that number one, it gets it scores just as well on the benchmark, the so-called linear cross entropy test, and number two, it does not require a large supercomputer. Right. Actually, just recently, I was interested to try to do look up the comparison. Right. If you look at the best current classical simulations of the Google Sycamore experiment, like by Pan, Chen, and Zhang, they use supercomputers that are probably using some megawatts of power, or that's what you would use if you wanted to simulate the experiment in a similar amount of time, like minutes or seconds or whatever. And so you could say maybe the ultimate resource here is just how much money are you spending for the electricity, right? So the classical supercomputer has a lot of cores, is using a lot of power. The quantum computer also has a dilution refrigerator, so that uses a fair amount of power as well. Okay, but the quantum computer wins, I believe, by some factor between 100 and 1,000. Okay, so that's kind of, I would say, the current practical situation in terms of spoofing the experiment. Now, there is this beautiful recent work by, Boaz Barak and others. There's been a previous Simon's colloquium about, but that work gives a polynomial-time algorithm, but it for classically simulating these RCS experiments. but it, it does not get a linear cross entropy score that is as good as the score that Google got, for example. Right now, it can only get about 10% of the excess of cross entropy that was observed in the experiment. Okay, so it's like a signal at the 0.02% level rather than 0.2%. Okay, so I think that like you could say, the claim of quantum supremacy, which was never an asymptotic claim from the beginning, right? It was only ever a claim about these specific numbers of qubits and so forth, right? That claim is still standing, but it is standing more precariously than many of us would like. Okay, it is of enormous interest now to try to do these experiments with better fidelity, which would allow you to scale up higher and and of course to think of better experiments, as was mentioned in the talk, such as ideally experiments where we could efficiently classically verify the results. So I do not regard quantum supremacy as a done deal by any means. Okay, so but what this work does, as I would say, like there, even after the insight of Gao and Duan, 6 years ago, it turns out that there remain some little loopholes by which, okay, maybe random circuit sampling could have given not just practical quantum supremacy, but scalable supremacy. So, for example, there was the possibility that with random circuits of logarithmic depth, that here, you'd be right in a sweet spot where you would still have a signal that you could observe that would be like a 1 over polynomial in n excess in linear cross entropy, and yet you would also have nice mixing properties and anti-concentration and so forth. So what this work has done is that it has killed that little lifeline, by which quantum, by which these experiments could have been scalable, which again was not the claim that was made for them, in the first place, but was kind of like, like it would have been an amazing bonus if that had been true, right? And so now we know that bonus is not to be had. And I think it's extremely interesting to ask now, kind of, is there any hope for, let's say a scalable speed up in, the NISQ model of computation? And, until a few months ago, I would have been much more hesitant to even say the NISQ model of computation. Like, what do you even mean by that? Right? It's just a practical term. But there is this beautiful recent work by Robert Huang and by Jordan Kotler and others, which has defined a complexity class that they called NISQ, which is somewhere in between BPP and BQP, right? Which basically captures what you can do with a quantum computer with a constant rate of noise, on every qubit, at every time step, combined with a noiseless classical computer, and not allowing for adaptive measurements. So, it seems like it is unclear, if you can do quantum error correction in this model. Okay, they do give oracle evidence that this model, at least in the black box setting, can be more powerful than BPP, than classical computation, but it's very, very unclear how to instantiate that oracle. Okay, and so now the question that we could ask is there a real world problem, either a sampling problem, a relation problem, or ideally maybe even a decision problem that is in NISQ, in this NISQ class, and that is not in BPP, right? And so what the work that Yunchao spoke about is, you might say, it is coming close to ruling out random circuit sampling as an example of that separating problem. Except as he alluded to in his talk, there is still, it seems to me, one loophole, which is that we could look at constant depth random quantum circuits, which are not spatially local, okay, and which have a constant rate of noise. Okay, these, as far as I know, we still do not know of any efficient classical simulation, and it is possible that even under constant noise, that these would still give you quantum sampling-based quantum supremacy in the limit as n gets large. Okay, of course, there's a practical problem, that you would require very non-local gates in order to implement it. Okay. Nevertheless, I now think it's become extremely interesting to know, well, is that really true? Is there an efficient classical simulation for, just a noisy, random, constant depth quantum circuits? So that's often one of the great benefits of a new result is that it brings open problems into clearer focus. And I feel like that is what's happened in this case with that problem. So, thanks.
Great, thanks, Scott. Sergio, do you have comments?
Yeah, thank you. Yeah, I also like this work. The main reason why I like it, I guess, is, well, maybe different than what Yunchao emphasized in the presentation. I think, the main reason why I like it is that it shows that in what we call the low noise regime, which is where the error per cycle is less than 1, so you don't have too many errors. It shows again in a very kind of nice way, which I think is kind of fundamental, that the computation remains hard. So the computation is, the cost of the computation is exponentially 1 over the noise. And I don't think I think that's quite fundamental. It shows very early on the proof. Is just that the polypass decay exponentially, right, in 1 over the noise. So that's what allows you to, is you keep the noise constant as you scale things up, you're going to get a polynomial algorithm. But before that, you cannot cancel polypaths, and I think you cannot cancel them for a fundamental reason, because that's where you have like the sign problem, basically. The polypaths are all going to come, with different signs, as they will do with Feynman paths or other, approximations. The same problem seems, shows up with when quantum mechanics is at play, let's say. So I don't think you're going to be able to cancel polypaths that have a weight, lower than 1 over noise. And I think, that's kind of one feature that I find very interesting about this work, how it shows that in the low noise regime, you still have a same problem and things like that. And that's other things break down if you try to go into that regime. Even the discrete error model doesn't work anymore. Interestingly, Yunchao in a previous paper also saw that. Just things break down if you have too much noise, and in particular, noise of, the error per cycle is more than 1. But several things break down, and this paper is another way of saying that, why you need to be in that regime. As Scott said, on the, if you keep noise constant and you scale up, I think, in my mind, I was not expecting that to work. I think we wrote that in 2016 when we introduced the paper that, complexity theory breaks down, as far as I could tell back in the day. We actually have a paper which we call Boundary of Quantum Supremacy, which we make the same statement, compared with different algorithms and making some approximations that, classical algorithms win if you just keep the noise constant. So that part I find, less intriguing, but the other part I think is a very nice, it's a very nice way to explain why things remain hard on the low noise regime. And then another thing in passing, I guess, I understand why the logarithmic depth, is interesting, because maybe there is a ray of hope there. There was a ray of hope for things being polynomial, but that's for hard random gates. And the reason why you get a bias is because you're using hard random gates. If you use the, so the result is, you can sample something which is not a uniform distribution, even with noise, if the depth is logarithmic, both in sort of an experiment, I guess, like according to that noise model, and also this algorithm. But that's for hard random gates. And the reason why it's not uniform is because you have this local bias, right? You have these, polypaths that they are like one poly per weight, which basically means there is like some local bias that it decreases exponentially in depth, and you can capture this local bias because it's local, it's not like entanglement. If you use the gates we use in the experiment that entangle faster, you will not have this local bias. So even at logarithmic depth in polynomial time, you will sample from the uniform distribution, the local bias disappears. I think that is more a feature of hard random gates than anything else. And it's just because hard random gates don't meet entanglement as fast as sort of the gates we fine-tune in the experiment to spread entanglement faster.
So sorry, Sergio, I didn't quite understand. So are you saying that with the specific gate set that the convergence to uniform happens faster or slower?
Faster.
I didn't quite follow. Faster. So you cannot even have as much depth. So you get more noise. It becomes. So you have to have an even smaller depth to get a signal, is what you're saying, if you don't have R random.
Yeah, this bias is just. I think it goes both ways. Why you have a bias, why it's just with hard random. 2-qubit hard random gates, right? You can project like X into X, I think is one of the examples in your papers or something like that. I mean, there is like some tiny bias on the X direction or on the Z direction. And if you're doing 2-qubit hard random gates, that bias disappears exponentially in depth, but it's always there. And so that means you're not converging to uniform as fast. And so even when you have noise, you might have some signal which is not uniform, but that's because it's just a local bias. You're not entangling things as fast. What you're looking there is at the thing that is not being entangled. It's just some local correlation. And in our gates, the one we use in the experiment, which are sort of optimized to spread entanglement faster, this doesn't happen. So you wouldn't have this bias even at logarithmic depth. Yeah. Or another way to put it is if you constrain yourself, in logarithmic depth, to a polynomial algorithm, then your algorithm will still sample from the uniform distribution, but the experiment will also converge faster to uniform distribution, so it's all consistent.
Mm-hmm. Okay, great. Well, thanks, Sergio. Adam, do you have?
Yeah, sure. So first of all, thanks, Yunchao, for a great talk and for the wonderful comments from Scott and Sergio. I'll just add a few additional comments. So that there are really a lot of different aspects of this result that one can discuss. But I think it kind of gives us a few different lessons to chew on as kind of quantum complexity theorists. The first is that kind of as a result of this paper, one needs to be very careful about stating what asymptotic regime one is in when one makes certain claims about quantum advantage from certain experiments. So, as we've seen already, sometimes we're making non-asymptotic statements about 53 qubits. Sometimes we're making asymptotic statements about various sorts of noise regimes. And this kind of needs to be very carefully kind of stated in kind of results going forward, especially since a lot of the prior evidence for hardness of RCS is really in a very low noise regime where there's a lot of signal in the experiment, like 99% signal in an experiment as you scale n, whereas actually the experiments are conducted in much higher noise regimes. So that's kind of one nice lesson I think we should take from this work. A second thing is I think maybe it invites us to reconsider some of our intuition for hardness of RCS in the first place. So a lot of the complexity theoretic evidence for hardness of RCS has its roots in earlier work in quantum complexity theory on the hardness of quantum Fourier sampling or Fourier fishing, where the problem is you're given a random black box Boolean function f and you want to sample heavy Fourier coefficients from f. And Scott showed back in 2010 that at least in this relativized problem, that this problem lies outside pH. One can view a lot of both these results of about boson sampling and IQP and RCS as trying to recover these results in sort of a white box model. And one can also view this Fourier sampling intuition as kind of the basis of believing hardness of tasks like Hog as well. Like in some sense, the heavy output generation task for random circuits is basically the exact analog of Fourier fishing for random Boolean functions. And in some sense, the validity of Hog, it could be rested on Quoth, like it was in Scott and Liegier's nice paper on the topic. But one could also think of the intuition here as coming from the fact of maybe viewing RCS as a heuristic implementation of Fourier sampling, where you say, well, look, a random Boolean function has some heavy outputs and light outputs distributed in some kind of exponential distribution. Well, the outputs of a random circuit look something very similar. There's some slightly heavier ones, some slightly light ones. And if you think this kind of analog of a Fourier spectrum of a random function, like if you think this analog for RCS is extremely unstructured in some sense, then you might believe that this problem is hard. And what the result Yunchao talked about, as well as kind of prior results of the Galadol result from 2021, is saying that actually random circuits, their Fourier spectrum actually has a bit more structure to it, particularly in the low depth regime. So if you have very low depth circuits, in some sense, it's easier to guess which Fourier coefficients are heavy versus light than it is for a random Boolean function. So I think that this is kind of inviting us to reconsider this and say, okay, well, in what depth regimes then is even what would we think RCS is hard to sample even in lower noise regimes? So I think there are a lot of really nice open problems that this work brings up kind of in this direction.
Oh, thanks, Adam. Those are great comments, really insightful from all of you. It's that's really interesting. Maybe
I can.
Yeah.
So Scott mentioned this open problem of sampling from a constant depth random circuit. So I think currently the complexity of that problem is unknown, even with, for example, a 3D architecture. But the problem here is that there is a sort of a complementary argument to anti-concentration with saying that if we go below log depth, then it's actually highly concentrated rather than just being not anti-concentrated. So which means that if we just sample from a constant depth random circuit, the output is highly concentrated. And that could bring several problems. In particular, one problem is that it would be hard to perform statistical verification. And also one would intuitively expect that if it's such heavily concentrated, maybe there could be some way to simulate. Although, sure, that technique is still an open question. And it's really...
Yunchao, I would like to quickly interject that that's kind of an architecture-dependent statement. So like, for example, if you take certain constant depth architectures, like based on measurement-based quantum computing, where you prepare a cluster state and then measure in the very special basis that does teleportation, then one has anti-concentration. These circuits are not simulable by the Napadol results because they're considering just a different circuit ensemble. So I think really this opens up that there are a lot of different architectures of low depth RCS one could consider, and the various fragments of these statements are true or not true in different models of them. And so I kind of view it as like there's a whole landscape to kind of sort out here.
So can I ask a question, Adam? So once you go to a measurement-based model, then you're relying on your input to be entangled in a certain way. So is there a natural notion there of what it means to be noisy in that case? Should we start with a perfect initial state and say brickwork state, whatever, and then start with a constant depth of noisy gate? So what would the fair model be then?
Well, I think the most realistic model would be you have noise in the preparation of the cluster state as well. So you'll Hadamard all your qubits, and then you have noise, those are noisy, and then you have noisy CZs on them, and then you perform these noisy measurements, right? So and I don't know how much is known about the complexity of this exact this exact model, because it's not a standard RCS model, because the ensemble of measurements you make is in the like HRZ of theta basis. It's just this like one parameter circle of measurements on the block sphere that you make. In the Nafadal paper, they are considering a slightly different ensemble where you measure in a Haar random 1 qubit basis. And the behavior of those circuits is really, really quite different, actually. So.
Yeah, I agree. So I should clarify that my earlier remark is entirely conditioned on using Haar random gates in the constant depth circuit. Surely MPQC is a different problem. And one way to think about that, it might be to think of it as the effective random circuit in a lower dimension. So if we consider 2D RCS with MPQC, then one could study the complexity of the effective 1+1D RCS. And maybe our result could be applicable in that context. Okay, and then Sergio mentioned this. Okay, sorry, go on.
Go ahead.
Okay, so Sergio mentioned this very interesting open question, which is, could there be a family of random circuits for which the convergence to uniform is faster than 2 to the minus d? So I think this is really open problem that is very interesting, and it will be really interesting to study these type of circuits and the complexity of RCS with that.
Well, I said with our gates is faster. I mean, yeah. I mean, if you study them using the techniques in your paper, so we did some of that in a paper on information scrambling on the appendix. We also work on the polybases. Your Alainer and Costi and everything work on that. You see on your polypaths, you don't have terms like x to x ever, which is what gives you the, exponential decay in depth. It always multiplies the polys, right? The polys just keep multiplying because that's kind of what needs to more. So then all the paths, even at log and depth, if it's in a fully connected architecture, all the paths will be having weight order n.
Yeah, exactly. So that's a very interesting observation. Although I should clarify that the information scrambling gate set is slightly different from the 2019 quantum supremacy gate set, because the quantum supremacy gate set has these continuous FSIM gates that with different parameters, and those actually creates a bias for the polypass in order to be exponentially small in D. So yeah, so there's a slight difference between the quantum supremacy experiment and the information scrambling experiment. Of course, it's very interesting study what's the complexity of the type of circuits considered in the scrambling experiment. Yeah, and then Adam mentioned the random Boolean functions. So clearly, hugely different from random circuits, because we sort of learned from our work is that random circuits really have a lot of structure. If you look at how the gates interact on top of each other and how the depth plays a role in the polypass. So that's really, so clearly, yeah, I agree that one cannot think about random circuits as random Boolean functions.
Yeah, in some sense, the analogy is that okay, with a random Boolean function, all the entries are plus or minus 1, and so kind of unless you see a ton of the entries, you have no idea if this Fourier coefficient will be heavy or light. But here, kind of the analogous quantity is the Feynman pass. Those are the things that are easy to compute, and somehow you're showing that actually just looking at a few of them, only a few of them really matter here, particularly in the low depth regime. But of course, as the depth runs, then this becomes less and less structured. So, yeah.
But again, this is crucially a statement about the noisy regime, right? This is, I mean, if we did Fourier fishing, but also with a constant rate of noise, right? Well, it's not exactly what we mean by that, because it's an oracular problem. But certainly, if the function had to be computed by a circuit, and each gate in the circuit were subject to that noise, then that would again become easy to simulate, right? So I think the noise plays a crucial role. I wanted to say that one thing that I'm not worried about at all here is the choice of gate set. I'll just, I think let's just completely grant the assumption that the choice of gate set, is not going to matter. I mean, that seems like a technical problem to, maybe, a worthwhile problem, but, extend the result to the type of gate set that Google used in its experiment. Let's just assume that that can be done, right? I think the real heart of the issue is about, sort of practical quantum supremacy versus the asymptotic regime.
There seems to be some, in the chat, some questions from the audience about for the panel. So, do you want to speak up and say?
Oh, so Zeph is asking, can we brainstorm about what might be a new task where the interplay between experiment and theory might thrive?
Well, I guess I can. Go ahead.
Go ahead.
Or I was going to say, well, one was, mentioned by Yunchao on the talk, which is trying to do something which for random circuit supremacy, as experiments progress, that can be based on, ideally more like a stronger cryptographic assumptions, and where the verification won't require these exponential computational resources as it does on random circuit sampling or Boson sampling or tasks like this. So there's, certainly interesting work in that direction. And yeah, hardware, experiments keep progressing. The requirements to do an implementation also keep decreasing. So hopefully, those two things will meet at some nearby point, maybe in a few years before we have a full blown up, quantum computer with a T-gate factory and all things like that. So I think that's very interesting. And in general, in NISC, I guess, well, moving outside, random circuit sampling, which might have applications in randomness generations and things like that, but maybe on other applications which have more, can be of more interest, like in physics or something like that, like trying to see what are problems of interest in some community that maybe we can implement in a quantum computer, like as some observable for a interesting physics problem that maybe we can, implement on a quantum simulator. And then, well, there is always going to be like this competition between classical algorithms and what we can do in an, on an experiment with noise and things like that. So I think it's also interesting to, keep studying those questions, like making them more concrete in terms of, well, a concrete proposal like here is an observable for some problem that we can maybe implement. In my case, I care about, random superconducting qubits, sorry. So they become a very interesting, controllable physics experiments, right? So what kind of problems can we try to address with them that are interested, not just from a computational point of view, but also that they give an answer to an interesting problem in some area. But at the same time, how do we know that, it cannot be approximated by smart classical algorithms?
Yeah, I'll just add that the thing that Yunchao already mentioned about trying to find cryptographic proofs of quantumness that might be feasible on kind of an intermediate scale device is a really nice question, and it's really not obvious whether or not it's possible to do this, kind of both from an experimental side of can you get X qubits or Y depth, but also kind of from a theoretical side. Like there's a wonderful question of like, do any of these like LWE based proofs of quantumness, would any of them survive in an asymptotic regime with constant noise rate? That seems like that it would be quite challenging to get something like that to work. But if one were able to do that, it would be extremely interesting. So.
There's also something that Sergio just mentioned, which is, hinted at, which is this this question, can one use this sort of these questions of quantum supremacy, quantum advantage to actually explore new physics, in the sense that, what does it take to say, here's some interesting physics where one can make a plausibility argument that this is physics that would not have been, easy to compute, and so in a sense, if it's new physics that, if it's not easy to compute, we couldn't have possibly explored it before, before having these kinds of experiments, because, well, we couldn't have solved it in closed form, we couldn't have guessed at a solution, we couldn't have simulated it on a classical computer. So, here's really a new kind of physics. So that might be something interesting to think about. So Sergio, did you have more to say about that? Am I reading too much into it, or?
Well, I don't know if I have a lot to say. I mean, of course, people works on approximation algorithms. You have some work on MPS, the MRG kind of algorithm, so which is specific to 1D, that gives us an idea that what kind of problems in 1D it will be dangerous to claim that we can do, something in an experiment that is not simulatable, because DMRG is a fairly powerful algorithm in 1D, and there are versions expanding that to 2D and 3D. There is interesting work on that as well. But that's just one direction. There is the same problem, which I think shows up in the work that we were discussing today. Again, like the polypass with a Hamming weight less than, 1 over noise. I think there is a sign problem there, so people are aware that there is a sign problem generally speaking. But there are probably other ways to think about it, come up with with reasons that problems are hard to do, to simulate classically, and try to make like concrete proposals that we can implement in current noisy devices. I guess we have people working on it more on like in the physics team, for sure, but yeah.
Yeah, and in kind of a related direction, there are also great questions as, in what sense is RCS a useful benchmark for experimental devices going forward? That is getting a certain RCS score really testing that you've made an integrated quantum device where all the individual components that work on their own, that they're actually all working together. In some sense, actually, the prior paper of Gao et al. From 2021 actually called this into question, perhaps even more than the paper that Yunchao was just talking about, just because in that algorithm, the way that you got a non-trivial XEV score was by just chopping up the circuit into different subregions and pretending the circuits didn't even interact with one another in the first place. And this is really kind of, that if that were to happen in your experimental device, it would be saying, oh, it really, just did not integrate. Some of your qubit lines were just totally broken or something like this. So I think there's also, some nice questions about, our kind of, are there algorithms that challenge quantum advantage, getting the quantum advantage from low scores that look kind of like physical processes that you would worry might be occurring in your experimental device? And the Gao et al. Algorithm is an example of one of these, but I think it's a nice question if there are more of these out there.
Yeah, interesting. Any other remarks or thoughts? So, thanks very much. This was very very stimulating, very interesting discussion. Thanks for all your comments, and thanks Yunchao for the talk. So, and thanks to the audience for skipping the soccer match, which you can now hopefully resume. And
Brendan Aaronson is playing for the US. You know that?
Tell me
Yeah,
about that.
Yeah, he's completely clobbering me in Google search results. I just checked. Yeah, so yeah, I'll have to go root for him, I suppose.
Okay. Any relation?
No, I don't think so. No.
Okay.
I mean, if you go far back enough, then you know.
Yeah. Great.
Yeah. All right.
Okay. Okay.
All right.
I'll see you all next week.
Yep. Okay. Bye.
Bye. Bye.